Yes, I am pushing the record button and we are good to go. So yes, you guys take it away.
Okay. I think you all can see me right now. I'm the one that you should be able to see. I'm Stacy. I do 4-H and FCS in Osage County. I'm gonna be the lady behind the Zoom today. Rick has asked that if you have questions to wait till the end. You can go ahead and put them in the chat if you want to, but we won't stop. We'll just keep going and Rick will answer your questions at the end. Cheyenne's gonna be on the Zoom controls. And then we have Rick and our county recreation leader, Jacqueline, with us today, and they're going to start working with you, learning some liquid nitrogen.
Yeah, it's just
Barely.
Everyone else muted. All right, so welcome. We're going to do, some of you might have seen this before. We're going to talk about the phases of matter using liquid nitrogen to show that. So one of the things we always start off with is we're going to show you how different elements, how different nutrients, that's a bad word. I don't know why. But anyway, we're going to show you how elements react at different temperatures. Like liquid nitrogen is at 325 degrees below zero. So Jack, what temperature does water boil?
I don't know.
212 degrees above zero. So that's over 500 degrees below between where water boils and where liquid nitrogen is still a liquid. So we're going to talk about that's true for all elements, or all elements like on the periodic table. They all have different properties, but they look the same. It just happens at different temperatures, different pressures, under different atmospheric conditions. Like, so there's three phases of matter, the main ones. There's kind of five, but we're going to talk about three mainly. There's a plasma, which is like the sun, which happens crazy hot, and you're going to have all kinds of magnetic stuff going on. So we're not going to talk about that. But the three in the middle are a vapor, like a gas, and then a solid, or excuse me, a liquid, and then a solid down low. And then the very coolest one, which is near absolute zero, is called a Bose-Einstein condensate. And it's like 459 degrees below zero is where absolute zero is. So we're not going to talk about that one either because we can't quite get there. So we got liquid nitrogen, 325 degrees. What happens? I'm going to talk about boiling points, freezing points. Those are all the places where matter changes phases. So I'm going to put some liquid nitrogen in this teapot and we'll see what happens. You know what the teapot is normally used for? So Jack's going to put that on there. So why is that with this one? Is that hot, Jack, or cold? You expect it to be, if you're used to a teapot, if you like tea, got any tea drinkers out there, you make tea by boiling water, right, at 212 degrees. Well, this is obviously not 212 degrees boiling. There's no fire under it. It's just the heat of the pot itself is causing that liquid nitrogen to go through a phase change to boil. It's going from a liquid to a gas. So if we would cool it back down, it would go to a liquid. And after a while, we're going to try to cool the liquid nitrogen down even more in a vacuum and see if we can make solid liquid nitrogen. Kind of one of the things we've got coming up. I'll put some. I'm going to put some liquid nitrogen in a 2-liter bottle. And Jack's going to put a balloon at the top of it. Any predictions? What do you think is going to happen? Because this liquid nitrogen is going through a phase change. It's going from a liquid to a gas just in the heat of the liquid of the bottle. So why is that happening? That was a weak soft balloon there. Try another one. So the liquid nitrogen is going through a phase change. So are there more atoms in there inside the bottle, inside this contained chamber of the balloon than when we started, or they're the same? Is what one of the points you're trying to make. Are there more or less or the same? And they're the same, it's just that there's less space in between each individual molecule or atom of nitrogen. And as it goes through that phase change, it expanded. When you heat things up, they expand. The actual atoms get farther apart. There's more energy in the system. So that it's the same amount, just like, so now we've got this. Can you zoom in on this? Cheyenne?
Yes.
We've got this middle bucket full of liquid nitrogen. We put, how many balloons do you think fully inflated can we put in there? So we're going to kind of show you that as we're pulling them out. And this is a fully inflated balloon. But what happens to it as we warm it back up from 320 degrees below zero? Can you see it okay?
Yeah, it looks good.
So it's going through a phase change. Actually, it's not going through a phase change, it's just warming back up. And there's a little bit of liquid in there. And so we've got one in there. We'll kind of go through this the whole time, but I'm going to hold this up now. And I want Cheyenne to get a close up and look down here at the bottom. Can you see the liquid that's in there? That is actually liquid oxygen is in there. That is condensated out of the atmosphere. There's two. See if we can get a better look here. There you can see.
Yeah, you can see it.
Yep, you can see
The
it.
liquid right there, and that's liquid oxygen. And how do we know it's not, say, liquid spit? Whoever blew this up, put water in there, right? Well, what temperature does water freeze? And this is a liquid. Water freezes at 32 degrees, right? Fahrenheit. Liquid nitrogen is 320 degrees, trying to hold it still. There's three. Liquid nitrogen. We've got two more in here. Liquid nitrogen is a liquid at 320 degrees below zero, so we know that that can't be water because it would be frozen. Is that good? So we'll pull a few more out of here. They're a little cold. So they're heating back up. So when we start with one, kind of zoom out now, just shine.
Okay.
There's all kinds of crackling going on. All right, can you see the one that Jack had? And then this one, they're both the same size, they both have the same number of atoms in them. It's just that these atoms are cooler, so they're closer together, they're condensated, they're concentrated, they're closer together than the atoms in this balloon. And that way, and there's just a different, and that's the same is true for every element, that they condensate, they concentrate as they warm, as they cool down, as they warm up, they get farther apart. So we'll keep pulling a few more out there as we go. Now we're going to set up for the next thing. Kind of one that kind of goes along with that is we're going to show you some, I'm going to put some liquid nitrogen in a Coke bottle. Can you see that, Cheyenne?
Yes. Excuse me.
Light a candle, right? So what three things do you need for a candle, for a flame, right? You need heat, which is the flame. You need a fuel, which is like our wick right here. And you need oxygen. So you've all probably seen where we take an oxygen, or you take a jar and you put a match in it and you close it down. We'll close it down and see if we can kind of get it to start fading. And you'll see that as it fades. Now I'm going to take I don't put on that. While she's doing that, can you see this? See this line on this? I'm gonna put a little more in there. So we've got the liquid nitrogen inside this Coke bottle, and just like on a cold day when you've got a regular bottle of Coke and it's like 32 degrees and it condensates on the outside, that's water. Well, here we actually have oxygen from the atmosphere condensating on the side here. You can see the drips falling. Look right down here where my finger is, Cheyenne. It's hard to see them. You can tell if there's a drop hitting there. So now put the lid back on, Jack. And I'm gonna drop these drops down here and watch the brightness. So you got the brightness of the candle, Cheyenne.
Yes.
So you can see as the oxygen goes in there, you can see the flame get brighter. Do you see that?
Yeah.
So that's just oxygen. That our atmosphere is 18% oxygen, 78% nitrogen. So is think about the question, is nitrogen poisonous or flammable? So you see that happening. And actually, this is if you're a space historian, the Apollo 1 tragedy that happened with the astronauts being killed because of a fire in their capsule while they were still on the launch pad was because of they used pure oxygen for the astronauts to breathe instead of an atmosphere that would be 12% or 18% oxygen like our natural environment. And things burn really easy when it's pure oxygen, and their capsule got a little electrical fire in it. It just burned up the whole capsule just really quick because it was a pure oxygen environment. All right. Do that.
Rick, we might should come with a disclaimer. Do not try this at home.
Do not try this at home. So I'm gonna I've got 3 different metal rods here. This is a brass rod, aluminum one, and a steel. We're gonna see how they conduct. We're gonna set those in there and see how they conduct electricity later on. We're also gonna take, I just got a regular bouncy ball. We'll see how it changes its properties, putting it in the liquid nitrogen. Yeah, you can blow it out. So we're set that aside and let it cool off and pull this set up another experiment here. So now we're gonna show you how superconductors work. This is the magnet you see in the middle is just a normal, the neodymium magnets you get that are really strong, right? They're stronger than normal ceramic kind of magnets, but underneath it is a superconductor. It's called made of yttrium, barium, copper oxide, I believe it's the full thing, but it repels magnetic field when it becomes a superconductor. And this is kind of the next big thing that scientists are trying to discover. Like it's how the bullet trains work. Like when you use your phone for a long time, it gets hot. When you use your laptop, it gets hot because of all the circuits working in it, the battery life working in it. So they're trying to figure out a way to dissipate that energy. So I'm going to show you what happens when we cool a superconductor down. So the superconductor is the black disc, and it's gotten broke, so we might have to put it back together. And then on top of it is just a normal magnet. So keep an eye on the magnet. And what happens to around the magnet is a magnetic field that goes. It's like wind coming off of it almost. Except it's a magnetic field. Same part. So watch what happens now. That's why I already did it now. So you see how that's floating? Because the magnetic field is not being allowed to go through that superconductor because it changes its conductivity properties as it cools down. So this is at 325 degrees below zero, so you know it's kind of hard to maintain those. Like they're trying to figure this out. This for our electrical grid system, the electricity that serves your house. There's friction in the lines that run across the country. And if they could figure out a way to do it without any friction, like a superconductor would, they would save a lot of energy and be able to produce energy cheaper. So this is kind of one of the next things that scientists are really looking at, trying to figure out why it does that and how to use some other things that don't have other elements that have the same property at warmer temperatures. So watch it as it warms up and you'll see it drop back down.
Why is it spinning?
Because it just has no friction against it. And we can make it spin if I can touch it without knocking it off.
Oh no, tragedy has struck.
So you can see it spinning there. Because it just has no friction against it, and its own magnetic field is being repelled by the superconductor holding it up in the air. So you can tell it that. All right, so now we're gonna do some things in a vacuum. We're gonna set up a different experiment. We'll let that go. Or we'll pull our old one back over here. So here you see.
Right.
Lower my voice.
No, slow down.
Slow down. I'm getting confused. So we got three metal rods there. This one is aluminum, then this is steel, and then this is brass. So you see the difference in the condensate that conducted the cool. This is just water vapor that's condensated on the side that conducted the coolness clear up through there. You see that the aluminum did it a lot faster than the steel, then the brass was in between. And that just shows you the difference in different metals, their different conductivity properties that they have because of just their makeup and how the protons, electrons, all the different, the nucleus comes in and how they're arranged on the periodic table can help you predict what those properties are going to be. We'll get the bouncing ball out of there. I can grab it. So what's the prediction for it?
You guys can feel free to answer some of his questions when he asks them.
So here, you got this in frame.
Yep.
I'm gonna drop it, listen to the sound of it. How much bounce there is there?
No.
We took the bouncy out of the bouncy ball. Here's a regular one.
That sounds tragic.
225 degrees below zero. It loses that elasticity and loses its bouncing. Which when it warms back up, it will be just like it was. Those properties will return. I'm going to set up a vacuum chamber now. So we live, there's atmospheric pressure, if you know what that is, from we live in an atmosphere, right? That's approximately 50 to 60 miles deep. High on the earth is the air we breathe. So there's pressure on us from that air pushing down, and that's roughly 15 pounds PSI per square inch, 15 pounds of pressure for every square inch pushing down on everything at sea level. The higher you get, the less dense the atmosphere, so the less atmosphere, the less pressure you're going to have. So I'm going to show you how those things change with a few little experiments. So I've got hooked up. So it's kind of like if something falls into the ocean and goes 2 miles deep, there's so much pressure on it, it will just crush anything. It will crush a ship, it will crush a person, it will crush most even whales that go that deep. Not much marine life can live that deep in the ocean. So it's even, so I just got a plain water bottle here. I'm going to crunch it up a little bit. Then we're going to put it in a vacuum and see what happens. Did I force all the air out of it or not? Or do you still have some pressure in there? It seems like all the pressure is gone. Jack, would you turn on the vacuum pump? And then we're going to see what happens. Why is it doing that, right? Because there's less pressure inside the chamber than there is inside the water bottle. The water bottle, even though we forced most of the volume out of it, it still had roughly 15 pounds of PSI in it. And that's what, once we took the inside the chamber, it's zero. There's nothing pushing against it at all. No air. Like it's hard to imagine air having pressure, but just like when you hang out a window of a car going 50 miles an hour, it blows against it, it pushes it. And that's the same thing that's being demonstrated here. The faster you go, the more pressure on your hand out the window. So this is the same thing. There's no pressure inside the vacuum chamber to hold the bottle in. Even though I've crunched it up, there's the same number of atoms inside the water bottle as when we started. It's just that they're farther apart now and they're pushing out. So if I cut off our vacuum, what do you think will happen? So it just goes back to where it was. The same thing would happen if we start to pump it back up again. Same thing's going to happen. I've got more balloons in here while that's doing that. So turn that off and we'll just start again. So one of the cool things I think about pressure is that you can change the boiling point of something. Back into that water. With normal water, we're going to pull a vacuum on it. Any predictions on what's going to happen when we lower the pressure, the vapor pressure it's called, on this water? Water boils at what temperature? 212 degrees Fahrenheit. Let's keep an eye on this and see what's going to happen. We're lowering the pressure, holding the molecules pushing down on it. When they have less pushing against them, they do what? We'll see here. A little bit. Patience.
Yeah, Rick, patience.
Patience. I have no patience.
We're well aware.
Let's go.
2.
So 2 o'clock.
Yes.
What's it doing there? Yep. Starting to do what? Starting to go through a phase change from a liquid to a gas, right? It's warming up or removing those warmest molecules from the water, and it's starting to boil at just room temperature. If you've ever been hiking in the mountains like at 15,000 feet, water boils at a lower temperature at that altitude than it does at sea level, or what we're used to in Oklahoma. And here you see, that's demonstrating that right here. At zero vacuum, the water, there's no vapor pressure pushing, holding it together, so it's able to boil. And it's not hot at all. Not hot, still room temperature. So another thing I like to do to show how you got me zoomed out here.
Yes.
This is called a Hero engine. I'm gonna fill it up, put some liquid nitrogen in it back, but like 4,000 years ago, I don't know, maybe not quite that long ago, 3,000 maybe, a Greek guy, maybe it's about 2,500 to get my facts straight. A Greek guy named Herodian came up with the idea. He had a metal pot, he put 2 vents in it and put them at an angle, that he filled it with water and put it over a fire and boiled it. And it's like the water vapor coming out, the steam coming out, made that pot spin. So we're going to demonstrate doing that same thing, but instead of water, we're going to use liquid nitrogen. Instead of a fire for heat, we're just going to have the heat of the bottle itself. So even today, our nuclear aircraft carriers, nuclear powered submarines, they still use steam engines. They just use nuclear fuel. So steam engines are there's so much energy, so much power that can be harnessed, that can be used for work when you use those phase changes of matter going from one phase to another. I'm going to warm this up.
You better put your safety glasses on.
Well, I gotta do this fast. not working as well as it used to. But I've got holes, small holes in here. Let's see what we can heat it up a little bit. That was amazing, wasn't it? Usually it spins really fast like that, and I didn't quite get it back together before it warmed back up. You can tell now it's kind of doing it itself, but we'll try it later. I'll warm it back up and see, but I didn't pull that off very well. Here we've got the liquid nitrogen that's going through the phase change. That the liquid is going through a phase change, boiling, and it's got pressure, right? You see the pressure coming out. That's pure nitrogen gas coming over the top, and as it reacts with the air, it condensates the water out of it. So what three things did we discuss when we need a fire? So this usually just makes a little. You got your glasses on? I'll close one eye. So we're gonna, three things we need for fire, right? A fuel like a match, a fuel, a heat source like a match, excuse me, a fuel, and then oxygen. So what's gonna happen when we lower this down in there? Any prediction? Why is it doing that? Or it burns my finger. We can put it out because there's pure nitrogen, there's no oxygen down below the level of this cup to let it burn with. So you can actually, you're not supposed to, you don't want to haul liquid nitrogen inside a closed vehicle because it turns over, it can actually fill the whole vehicle up with nitrogen, gas nitrogen. It's not poisonous, it's just that it forces all the oxygen out of the air and you can suffocate that way. What else we got to do? So I'll show you real quick on some different pennies. So pennies made before 1982 were made out of solid copper. So I'm gonna hold these up there and see if Cheyenne I can hold them steady enough for Cheyenne to focus in on. And the ones made out after 1982 were made they were copper plated, but they had a zinc core. So you can see this. And so copper is very malleable. You can see I hit it with a hammer and smashed. It didn't break at all. So that was this penny is pure copper. So you see this one here that has a zinc core and just copper on the outside. Zinc is very brittle, and when it was hit with a hammer, it just broke. So this was done because copper became so valuable that they couldn't, there was more than a penny's worth of penny in a penny. So they had to find out a way to make pennies cheaper. So they just made the core zinc instead of copper.
Lead in your hands.
Up a little bit,
Go up a little bit.
right there. That's a lot better.
It's better than copper.
That's better. Right
That's
there.
it.
Can you see that? You can tell the one penny has been smashed. All right. What else you got on our list to do?
The vacuum.
Okay, so we'll see if this takes a while. We'll do some other things while this is running. We're going to try to make liquid nitrogen turn into a solid. You'll be able to see that.
I think so.
I think so.
Okay, if you would turn on the pump, please.
Good job.
So by putting liquid, it takes a while for this to happen, just like the water. So we'll keep an eye on it and talk about some other things while it's kind of running in the background. I'll make some Dippin' Dots. Normally we feed everybody while we're doing this. We got till 2.
Yeah, you want to do your cotton balls
Then we do cotton balls
In the Cheetos.
and the
and
Cheetos.
Cheetos.
Yep.
We gotta be real careful when you do this. So we're gonna, normally we feed you ice cream. We'll show you how to make some Dippin' Dots in a second with ice cream. And we also feed you Cheetos if we do this around. The next year comes around, maybe we'll do this and we'll be able to get something to eat. So we're gonna cool these off. That's good. We'll pour some nitrogen in here. So, let me eat something cold. We've done this, never do this with bananas. They have lots of moisture and they'll stick to your mouth. But you gotta put it between your teeth. You got a good shot
Yep.
and bite down on it.
Go to the nose.
Don't do it.
Looks like a dragon.
Yes.
You know what? No Jackie in it.
Just move to your right or left. There you go.
Crunch it. Don't start now. Whatever you do.
Jack's like,
It's too big. What happened to the ball?
I couldn't find it.
So, I don't know if my vacuum pump is good enough to get this solid, but it has to get really a perfect vacuum, and this is just a cheap vacuum pump. So hopefully it'll get there in a little bit.
I'm really excited
So
over
we
here.
got Cheetos. Move this to the side. We'll do Dippin' Dots. You focus on that.
Yeah.
Got it. So this is just, I've got just, that's just ice cream mix, water and half and sugar and vanilla. I'm gonna hold it up high above it and just dribble it, put drips down in it like if you've seen a. And the ice cream just freezes instantly. Forming those droplets in the falls. Kind of like Dippin' Dots, but not exactly. And then you just got these little gummy. Bring that out here on. It's really cold. Once you let them warm up a little bit, they're really good. They're really key to making good ice cream is to freeze it fast and not let it form ice crystals. Kind of like freeze or burn is mainly ice crystals, something that's been in the freezer a long time. So when you freeze this mix really fast, it's really creamy and good. So that's how we make Dippin' Dots. Well, you feed this to you too. If you come next year for Roundup. So we got any questions, Stacy?
I don't see any so far.
Anybody got questions? I went through this faster than I normally do. Got anything else I want to do?
You have your cotton balls if you want to do your cotton balls.
Switch down or break. And something.
Cotton ball, that's kind of weak.
It is, but you know.
Well, no questions.
No.
Guess we're done. Thanks for coming.
How many balloons did you have in there total, Jack?
Got 15 balloons in there, fit in that one middle bucket, completely inflated with air, except that it would have been a phase change of the gas down to the liquid from being cooled off. Thanks for watching.
I turned it off.
I still
No, I turned it. Or.
Yeah, you've got lots of thank yous.
That was awesome.
No
Thank
question.
you.
Thanks, Alex.
Thanks, Alex.
Thank y'all.
And we really will come see you at your county. We would love to come do this with you guys if that's something you want to do. And we'll totally make you ice cream and Cheetos and candy and bananas and whatever else you want. So get with your educator and be like, hey, I really want to do this. I really want some nitrogen ice cream. We'll totally come visit you.
That would be awesome. I will definitely promote that.
Yes, ma'am.
Yeah, since this is all science stuff, I definitely can promote that and get it out to all the counties. Alrighty, anything else you guys need from us?
I'm good.
Okay,
Thank you.
thank you guys. I think we have another, our last workshop Roundup workshops. It starts at 2 o'clock. So you guys can hang on tight for the next 20-ish minutes, or you guys can hop off and then come back on. It's up to you guys. But thank you guys.